Hope after yesterday's conference dinner, everybody is now fresh and eager to listen to the plenary of Ingrid. Well, it is my great pleasure and honor to introduce her talk, the talk of Ingrid Daubechies, who will tell us about the application of mathematical algorithms in art investigation. Ingrid's fundamental work on wavelet analysis is so well known to this audience, the Daubechies wavelets and breakthrough that her work made in image compression and in general in signal and image processing and analysis. Beyond wavelets, also her foundational work in the domain of sparse representation, optimization algorithms, has influenced and shaped the work of so many of us in this community. She is currently Distinguished Professor of Mathematics and Electrical Engineering at Duke University. Professor Daubechies has achieved many honors, among others as the first woman to receive a National Academy of Sciences Award in Mathematics, also the first woman president of the International Mathematical Union. Recently, last year, the Wolf Prize in Mathematics, also as the first woman ever to receive this prize. Well, she received so many other distinguished awards, and it would take too much time here to mention even a small part of those. I have been privileged to collaborate with Ingrid. We wrote some papers together and organized some workshops and seminars together. And I think I can say everyone who has ever been in contact with Ingrid knows her not only as amazing and brilliant, deep mind science, but also so full of positive energy and huge inspiration to her collaborators and students, always curious and really truly engaged in conversations and collaborations. Let me just add at the end, Ingrid was often asked about why and how she combines her work on pure mathematics and applications. And she said many times that she loves to work with people and to learn about problem, extracts the mathematical question, works on the mathematics, but always stimulated by application and trying to remain relevant to the application. I think this is a good advice also for all young researchers in this community, and I think this is also what we will see reflected in the talk of Ingrid that she will deliver now. So let me all welcome Ingrid.
Well, thank you. So I actually, I will be slightly different from what's in the abstract because I thought I wouldn't have time to prepare a new talk, but I actually did for Eusipco because as Alexander said, I am very motivated by applications, and so I thought I would tell you about the whole list of things in which I have been involved in using image processing and bringing then some mathematical ideas to bear on the application for art conservation. I was very thrilled to see the theme of this Eusipco because it's wonderful to be able to do things that then has an impact on a large group of people and not necessarily only through industrial applications. And that may inspire a next generation to say, oh my God, you can use math, you can use engineering for this. So here it goes. So these are the different topics that I hope to get to in my talk, and we'll see whether I get there. So the very first one is the first of the topics that I lay the 6 millimeters under. I mean, art conservators hate this name, but that's what I call her. I mean, we did this at the time that there was this television series of 6 feet under. So at the end, I'm always afraid that I'm going to forget names, so I actually have put Here all the names of all the collaborators, and some, if they repeated on other collaborations, I didn't repeat. But so please, all the people I've worked with, I've enjoyed working with hugely. In some of the collaborations, I really was more a cheerleader than the person doing the work. So that has been a huge, and some of them are here in the audience. So. Lady 6mm under. So about 15 years ago, this was the cover of the Journal of Analytical Chemistry. And it was because Joris Dick and Koen Janssen is a material scientist, had used what was then a very new technique, it's now become standard, infrared reflectography to infrared fluorescence reflectography to investigate a hidden image in a Van Gogh. So this is the painting by Van Gogh. If you then turn it on its sides, you get the patch of grass, and below it is this portrait. This portrait is from an earlier period in his career, when he was living in Nuenen, very early on when he was a painter, with his, at a familial home near his parents. And he was then painting lots of portraits of peasants in very poor light conditions, and he had a very dark palette, but he was trying to experiment with how he could render color with a limited palette like that. And this painting is something that one that intrigued the art conservators, because many paintings from this period are known, but during all his life, except a few months that he lived in Paris, Vincent van Gogh had a very sustained correspondence with his brother Theo van Gogh, and there's a letter in which he says, "I'm sending you to Paris a painting that in which I feel I particularly well succeeded in what I'm trying to do." And the letter has been preserved, but not the painting. Now, of course, once Vincent van Gogh came to Paris, he met the Impressionists. He changed his style completely. He became very exuberant in color and so on. And so it's not unlikely that this painting that he valued earlier was now something from a past that he didn't want to. And so, because he was poor and reused canvases a lot, about 30% of his paintings have something else underneath, he just covered it up and made a study. So, but they were interested in seeing what was there, since it's nice to know what he valued so much. So people had been interested in finding out more, and Koen Janssen and Joris Dick had proposed this as a first case study for using infrared fluorescence reflectography. And so what you do then is that you in very small portions, you excite with a high energy laser, and that ionizes a lot of atoms, and then you capture the spectrum of the fluorescence. So electrons fall back in two jumps, and the second jump has a very particular frequency that's dependent on the atom that you're looking at. So you get a spectrum that tells you how the concentration of those atoms at different places in the painting, and you get that through these wavelengths that you measure. And so, for instance, in arsine, which was a component in a wavelength characteristic for arsine, which was an element in the vermilion that Vincent van Gogh was using, you get the thing on the left. And in molybdenum, which was part of his Naples yellow, the only light component in his palette, you get the thing on the right. And so, since it was the only light component, it's a good stand-in for the luminescence of the painting. And so they used this to then colorize, and they got a much better impression, and so people were very excited by this. And this has become now a technique that is used standardly by art historians and art curators and conservators to investigate what's below the surface, together with X-ray and normal infrared. So Koen Janssen and Joris Dick heard another talk I gave, and very generously they said, look, you know more about image processing than we do. We just used Photoshop a little bit to colorize, but maybe you can do more. And they gave us the whole data cube. The first thing we noticed was that there were these very weird zigzag patterns. And I said, Joris, I don't know, what is this? We didn't see that in what you showed us. And they said, well, yes. So in order to get this high energy laser, they actually had negotiated to move the painting, because it was in Hoge Veluwe, where they don't have such a laser in the museum, to a teaching hospital in Amsterdam, where there was a synchrotron that was being used to make short-lived radioactive elements for medical uses mostly. So the day job of this laser was something completely different. But they're expensive experiments, and so typically the functioning of such a synchrotron is paid for partly by its medical job, but also partly by physicists who use the laser for experiments when it's not doing its medical job. And so it's usually set up so that the laser beam can also be used in a different, and it alternates between the two. And so they had rented this experimental space, and they had the painting there. Now the laser beam doesn't move from one spot to another, it's there. So what you have to do is you have to move the painting to get the laser at different spots, different pixels on the painting. And that had to be stopped every so often, that the laser was going to do what it should have been doing, the medical job, and then the laser would come back. And so there had been a problem in the synchrony of the stopping and advancing. And so they had lots of little breaks. And since the scanning was done in zigzag, the anomalies gave you then these zigzag things. So the dark spots are because the covering painting has impasto, and there might not have been enough energy to actually get the fluorescent spectrum through. And so those are the dark spots. But they're dark spots, they're not dark zebra paths. And so the first thing we had to do, I said, well, what did you do? He says, well, we took them line by line and we kind of faked it. And I said, well, we're not going to do that. So the first thing we had to do was to make a mathematical model for introducing breaks, because we didn't know where they were. I mean, some are very obvious, but there's smaller breaks elsewhere. And to find by Bayesian inference and optimizing, what we did is we minimized the variation. Clearly, when you have these dark spots in zebra split up like that, you have much more variation over the image than if they're nicely aligned and you have one dark spot. So we did that iteratively, and we got to a much nicer version before we could even do anything. Next, we were going to inpaint. I mean, all the dark spots, now that we knew where they were, and we knew very well where they were because we had used them for the first stage, we marked them and we inpainted. And the nice thing with this is that we had a whole hypercube, and so what we could do is find the optimal way of inpainting for versions where it was clear how to do it, and then do the same thing elsewhere. So we used a different algorithm for the very long stretches that had been masked by the grass impasto on the front, and so we marked those and inpainted those. Then after that we had a problem still in one eye, and we said, what should we do here? And the art conservator said, well, when we have paint losses in one eye, we use the other eye, because usually painters try to be. I said, oh, well, we can do that, and so we inpainted that. And so now we had inpainted, and we inpainted systematically the whole thing of the cube, and we could try to colorize. And the inpainting had worked very nicely and smoothly, and my student said that she thought this was the best algorithm ever to remove black spots in the face, but zwarte punten. But we had a problem, and the problem had been the same for the original colorization. We didn't really have in the spectrum all the different pigments represented. We didn't have things for blues or for the earth colors. So we didn't have enough information from the cube. However, we looked at other paintings by Van Gogh in that time, and here are two examples of paintings one with very little contrast and one with very high contrast. And if you then look at them in chromance, then they look very different because, well, where it's very dark, you don't really know whether it's very dark brown or very dark violet or very dark anything. So you really should discount all that dark stuff. And if you then also level contrast, you see that there's a lot of similarity, which means that we could use the partial information we had from the fluorescence, infrared fluorescence, together with all these other paintings to infer from the partial information we had, and we got to this version of the underpainting. So we went from the thing on the left to the thing on the right, and Joris Dick was very, very happy and we were very happy to have given more life to this, the face of. And it turns out that there's another painting that he probably made of the same model in Edinburgh, and that looks very much like this. But here he was using a darker palette. Okay, so that was Lady 6 millimeters under. She's actually not 6 millimeters under. 6 millimeters is a lot of paint, but she's a little less. But what happens with these and all, give this list in chronological order, is that when I give a talk about one of them, there's almost always somebody in the audience who says, you know, if you could help with this, then maybe you can help me with that. And so I was in Belgium for a sabbatical, and I talked about it with Maximilian Martens, and he said, you know, this in painting, we have an ongoing discussion about the altarpiece at Lam Gods of Jan van Eyck, Hubert and Jan van Eyck. And the discussion, this is a fantastic painting. It's if ever you are in Ghent, for people who know from Belgium, you have seen it, I'm sure. But people who haven't seen it, if you're in Ghent, you have to take time to go see it. It's extraordinary. It was really influential already in its time. Many painters came and to look at it, and there are many paintings, art historians have traced its influence in the art of its time. Anyway, so this is this altarpiece, which is gigantic when it's open. When it's closed, this is what it looks like. And Maximilian Martens was telling me about the scene in this Annunciation. You see behind Mary, there is this book. And he said that people are wondering whether this book was just little squiggles made by the painter to mimic a book, or whether he was really painting letters. I said, well, I mean, what's the problem with that? I mean, I can't read stuff like that, but you guys can. He said, you just look and you can read it, then it's a book. If you can't, he said, well, it's more complicated than that, he said, because it's full of craquelure, and that makes it hard for us to actually read it. And it turns out that there's we are very bad at thinking away things. We're good at finding patterns. And you all have seen this thing with the three Pac-Men that point at each other, and everybody sees the triangle that is not drawn there, but that we infer. So we're good at seeing things, at inferring, but we're very good at thinking away. Very bad at thinking. Our visual system is not good at thinking away stuff. And so I said, well, surely image processing can help. And it was actually much harder. I mean, and Alexandra knows this. I mean, what you have to do is find all the cracks and then remove them. And to finding the cracks is not just a question of saying, oh, it's this species of brown that we have to take away, because you have brown everywhere. And well, it became a good part of the PhD thesis of Bruno Cornelis, and since then Alexandra has told me one of her students has actually much better algorithms now, so it's still something that was worked on afterwards. And so instead of the cracks, all the cracks that you see here, we went from a text, the crack pattern was a crack flow identified. In practice, what happened in the thesis of Bruno Cornelis is that he used 3 different algorithms, which were all 3 reasonably successful, but not great. And instead of trying to find one that to make a very complicated one that would be even more successful, what he did was he did a majority vote of those. And that, of course, is something that we're all very used to these days. It's a philosophy that's used all the time in neural nets. That then was very good at identifying the cracks. And then once you have them, you do in painting, you use a standard, well, by now standard algorithms in image processing, typically by doing non-local diffusion in patch space. And they did the inpainting on the right. And actually, when first Bruno showed me this, I said, well, fat lot of good that has done to us, because it doesn't seem like you can read anything more. But that's because I can't read these things. To experts, it seemed much clearer. And so they were delighted, and this led to them to surmise all kinds of things, and which I have understood they're now questioning again, so probably we need to revisit the problem. So Alexandra is nodding, so we will do that. So that was this Annunciation scene. And I gave a talk about that soon after I joined Duke, and there were people in the audience of the North Carolina Museum of Art, and that led to this new project. So in all these projects, I mean, I'm showing you only images, and I'm in my what I say, I tell you the math and the algorithms that were developed. I had a colleague at Bell Labs who said, it's true that an image is worth 1,000 words, he says, but only if you have the 1,000 words. So I can assure you, I do have the 1,000 words. If you want to know the 1,000 words, see me afterwards, and I can give you lots of references. I mean, but I thought the images would be more interesting to show in a plenary talk, if I don't hit the microphone too much, than all these formulas. Okay, next project, Reunited. So this is by a long chalk, not as famous as Van Eyck. I mean, this is really a minor altarpiece of the 14th century was in a small church in Italy, which probably was decommissioned, and that's how the altarpiece got sold. And it got sold it got separated into different panels by the art dealer at the end of the 19th century who sold it to Samuel Kress. And that's how it came in the Kress collection at the North Carolina Museum of Art. Because, well, one altarpiece gets you more than a small painting does, but 9 small paintings get you more than one altarpiece. So very many of these were cut into pieces and then sold separately. So these 3 are in the North Carolina Museum of Art, and it was known, because it came from the same collection, that this panel in the Portland Art Museum was with it as well. And David Steele, who was the art curator for Italian art at the North Carolina Museum of Art, had discovered that the style and the punch marks, and we'll come back to punch marks, were the same as in these 3 panels that are part of the collection of the Metropolitan Art Museum, and this one, which is in the Art Institute in Chicago. And it became clear from analyzing the wood on the back that this is how they originally were assembled, and that there was one that was missing. And it's still missing. I mean, David Steele, after he realized this, they were part of the same altarpiece, looked everywhere, searched this one, and it's still missing. We probably will never find it. But after he had found that these things belong together, he was very interested in mounting an exhibit where they would all come together. And the other museums were not so interested, because they said, well, there's a missing one anyway. It won't be the full altarpiece. And upon which they decided to commission from Charlotte Kaspers, who's a fantastic artist in her own right, but who also is a trained art conservator, and she is a specialist of what she calls art reconstruction. That's to say, making copies of artworks, but not just copies, painting with exactly the same pigments, the same style, the same materials as the original painters. So she has been commissioned here. She's been commissioned by the museum in Maastricht to repaint Jeroen Bos. it's not because, what happens with these copies is that they're beautiful, very valuable for scientific research to see what you can see through things and so on, because you have several stages in between that you could photograph and document, but also for students or even children to manipulate, because, well, they're valuable, but they're not the priceless originals. So they commissioned her to make a painting of this missing panel. Well, but it's a missing panel, you don't have it, so you can't make a copy. But what they first did is they knew what the topic had to be, because the painting here shows the life, the small panels show the life of John the Evangelist as they are described in scenes that in the Golden Legend, the Legenda Aurea, which was a medieval bestseller. You know how many of these pre-book printing books, we only have portions of books and so on. Well, from this one, they have hundreds. I mean, everybody must have wanted it. And so they know what the missing scene was. And so she then made a composition by borrowing as many possible elements from other scenes. So it would be in the same pictographical vocabulary. It's completely different from the true one, if they ever find it, but it would not have surprised at its time. And that was the goal. And so she was commissioned to then make this. She documented it all. It was a process that took 6 months, because the preparation of the wood panel itself already takes many months. And then the painting itself took something like 6 weeks, all the layers. And at the end of it, there was this beautiful, vibrant new copy. I mean, with gleaming, because all these gold surfaces were polished. And so they would be shining and reflecting in the candles. They were like mirrors. And the punch marks, to which we will come back, were helping in making interesting reflections. And the colors were fresh and then they realized they would have a problem, of course. They made a documentary of its realization, which I still have. And because if they were to put it together with the old ones, everybody would have eyes only for the new one. This gleaming, wonderful, new, shiny object, which would be the only one that was not authentic. So that's where we came in. What we could do is we could use image analysis and image processing to study both the new one and the old one. And we had wonderful ways of, because Charlotte had used pieces of composition of the old the old panels, but with the same pigments, because they had a chemical analysis of those pigments, repainted. So we had many things of which we had exactly the same portion of fabric drapery, for instance, in one, and in old and new. So we really could look at that correspondence. And at that time also, painting was, she had followed a manual from the 14th century in painting, and for different color planes, what the handbook said was you would, for instance, for a blue robe, you would make your blue mixture, and then you would use also a darker color and a lighter color, and in order to make shade portions in your blue, you would make a little bit of the darker color mixed with your blue for the darker things, and then a little bit of the lighter color to make the light highlights in order to get a nice effect on your fabrics. And what that means, if you just think of it, think of the pigment that you've mixed, of the paint that you've mixed with the different pigments, as in RGB terms. So you have RGB in a small cloud in RGB space. And now you're adding to that, with varying intensity, a different RGB vector to make it darker or lighter. And the result is that in RGB space, and this really happens, you get a plane. Not if you look at all the pixels, but if you look at only the pixels of that blue robe, you get a very nice planar section of RGB space. And then if you looked at the old ones, you had a planar section. If you looked at new ones, you had also a planar section. And basically what happened was that things had moved. Sometimes there was a slight rotation, a slight adjustment. But so just finding how you move things in RGB space for each color segment separately, I mean, and that is something that you do not just by selecting RGB things, it's by selecting in the composition, so you have to segment your image. You could actually rejuvenate colors and or age colors. So what we did is we found how to age virtually these panels, this painting, and we did that. And so that was then printed in, we added crack patterns from the old paintings, and that was then displayed. It was a high quality print was made, and that was displayed. And here you actually see it more than you saw in reality, because this was a photograph taken with highlights for the photographer at the exhibit. And when those very strong lights weren't there, the difference in reflectance from the varnished paint and the shiny paper was not as strong, and you actually hardly could see a difference. To the point that when the curator who accompanied the painting from Chicago arrived to have the painting from Chicago installed, was angry with them. He said, "My God," he says, "you made a forgery. You realize what will happen?" He said, "No, he says, it's printed on paper." And so when he looked closely, he saw it. But so, I mean, from a distance, it fooled even a curator. So in the exhibit, they showed this reunited painting. They showed the new panel separately, together with all the materials that had been used to make the different pigments. And then the documentary of Charlotte painting this new panel. And then on the fourth wall, there was something else, because we realized that since we could virtually age the new panel, we could rejuvenate the old panel. The only element that we would need in addition to the change of color well, there were two elements that we would need. One was to detect and in-paint the cracks of the old panels, but we knew how to do that. We'd learned that in Ghent. And then we needed to also rejuvenate the gold leaf work. So let me show you. For the cracks, actually, again, the craquelure is very dense. And as I said, cracks it's not as easy as you might think to detect cracks and only cracks. But we did. We used what we had learned in Ghent to make the crack pattern to identify where the cracks were. And then we in-painted them in an iterative procedure which we let be steered by the conservators, because they were very concerned when we started talking about digital visualization that we would end up with a kind of chromo, which was not our goal at all. So we felt that we would let them tell us in the procedure when it was enough and not too far. And that's what we did. And so in the color remapping, so I'm going to remove the gold, because the gold is separate. We'll come to that. So here I have on the one hand the old 8th panel and the new 9th panel. And you see the robe of St. John is really copied on the 9th panel from how he holds his robe on the 8th panel. And so this is what we rejuvenate in color from the old colors in the 8th one, and this is how we age the color from the new one to an old version for the 9th panel. And this is something that the curators and the conservators were they were very impressed by how painter-like it still seemed, because we had preserved the nature of how a painting is made and what that does in digital space with these different vectors, and we just moved it to where evidence told us aging or rejuvenation would move things. For the crack generation so this is the 9th panel, aged, virtually aged, we just used the crack panel, because cracks form physically from an interplay between the surrounding atmosphere and humidity and so on, and the wood and the gesso and the pigments that you apply to it. And because those pigments are different in different areas of the painting, cracks form differently. So we borrowed those crack patterns and just moved them to the right places. And that looked very, so we did not try to mimic a physical cracking mechanism. That would have been much more arduous, more authentic in a sense, but was really not what the curators felt was needed. I mean, so since it wasn't, I mean, we borrowed enough from what happened in order to make this look realistic to curators, but we didn't try to mimic that aging process. We really did image processing. Then, for the background, we again borrowed from the other paintings in order to add that aged gold look, which was a goldish yellow with all the cracks and so on. Now, new gilding on the rejuvenated panels was a different matter, because all those paintings, as you see them now in museums, they have this yellow, and sometimes there's still a little bit of gleam, often there isn't. Also because varnish has been applied to it over time, and that has yellowed and cracked. But originally, they were really beautifully varnished. In fact, all the preparation of the layers of the wood to make the painting is to provide an incredibly smooth but slightly elastic layer on which you can apply gold leaf, and it gives you enough resistance that you can really burnish it and make it mirror-like, and that you can then put in punch marks. So you see the halo here around the head of John shows things. Well, those have been done with punch marks. So Charlotte had new punches made in order to make punch marks on this new rejuvenated, this new version of a Gissy panel, and you can see them in the old paintings. The art of the skill of the painter was in that with these punch marks he could make slight depression in the gold leaf, but not so strong that he would break the gold leaf. I mean, and gold was expensive, so these gold leaf layers are very thin. They were thicker then than they are now, but still. So you had to do it just enough that you had a slight indentation, that the profile the normals would be different at that place, and so the reflections would be different, but you didn't break the gold leaf. I mean, it then, because after all it did give stresses on this layer, was something where cracks formed more naturally. But so after that is done, so we had to find, in order to rejuvenate this, we had to find in every painting the location of the punch marks. But since it's always the same thing, you can actually do that by doing recognition algorithms. You can make a profile of what it should be and then find where is it likely to be, and you can make a punch map. And we now know how to do that. To be quite honest, for the Gissy, we did it manually. I mean, but you can easily, with image processing, and we can do that now, do this automatically. And it's not as easy as it sounds, because of course you don't get these curves beautifully already in a MATLAB version. I mean, but you do find them, and then you have to use that. Okay, so how do you make something look authentic now? With the paint, we just had to change an RGB space. But if you think of something gleaming, think of a silver spoon like at dinner yesterday. I mean, you see that that's silver because there's a curve, and you can see the reflections change depending on the angle of the light and so on. But when something is completely flat, it's actually harder. And we get impressions of the fact that it's a metallic surface because we move our head. And even when we don't move our head, our eyes do move a little bit and take into account the different impressions we get from those changes. It's harder to do that on a screen like that. So we experimented, and we decided we wouldn't be able to do that very well, except if we made things move. And if we modeled our paintings as 3D objects with which were flat, but which we used computer graphics techniques in order to then have reflect. So we didn't do a full rendering. We just did a change of normal in the places where we had punch marks. But since we had the punch marks in the right places, we could do that. And I'd like to queue up the... Est-ce que nous pourrions avoir la vidéo, s'il vous plaît, maintenant? So I have a little video that was shown on the fourth wall in the exhibit, where I'm going to show you. So this is the punch mark, and we used computer graphics techniques to model. La vidéo, s'il vous plaît? La voilà. So on the fourth wall, there was a very large screen, not as large as here, but still, that showed people what the effect would be with, this had all been done by undergrads, so if you say, oh my God, I can do better, yes, you can. But there were also little iPads with interviews of the undergrads who had done this. So, so you see how and people were entranced by the fact that you could do this with methods that were all justified by scientific research and elbow grease and mathematical thinking. And as a result, the exhibit became very, very popular. What they first thought would be something that would only be of interest to experts in an area became something to which docents to the museum would bring everybody who gave them 10 minutes extra. And people were very enthusiastic, and it inspired especially high school kids. I mean, because they sit on their computers all the time. And here was something that brought to life to them these paintings. Here you have a couple of comparisons one-to-one between, but it's static, so you don't see as much of the reflection. On peut terminer la vidéo maintenant, s'il vous plaît. Okay, that was GISI. I have a little bit of time still, so. During the GISI altarpiece thing, and the exhibit did travel to Portland, and after that, all the paintings went to their own homes again, and so now this exhibit only still lives virtually. But during that, we came into a different project, Platypus. So the genesis is that for the detailed study of these old panels, we wanted to see everything that was available, X-rays, infrared, whatever they had. And when we looked at the X-rays, so for instance this one, the X-ray looks like that. I said, what is that? It looks like this painting is in prison. And I said, yes, Noello Concert with a sigh. Says that's the cradle. I said, the what? The cradle. And in fact, I should have known before, because if you look at the Van Eyck paintings, of which you can see superb visions online with great resolution, and you look at their X-rays, you see cradling as well. And I said, what is that? And I said, well, this is something that was done in the 19th century and early 20th century, which is called cradling of paintings. So these paintings on thick wooden panels. These panels were typically an inch thick or so. So that wood worked. I mean, it's an organic material, depends on the humidity, but the whole painting techniques had been used to adapt to that. I mean, yes, it gives a little bit of cracking, but all these things worked with that. I mean, the painters knew that this was not going to destroy their painting. But when these paintings became part of art collections, they liked them flat on their walls. And so the mind boggles, but they would take these fantastic pieces of art and they would plane the back. Sometimes they did it, as in this case, you see a little bit of worm damage. Sometimes they did it to take away diseased wood, but most of the time it's just because they wanted them flat. And so they would plane them to a few millimeters thick, and then of course it became much more floppy. So then it needed to be strengthened. And they put on the back hardwood in one direction and tunneled it through in the other direction. And they called that the cradle. So that's cradling, or in French, say, parquetage of paintings. And of course, this was nice, solid hardwood. And you had just a few millimeters of painting. So when later they discovered that X-rays were really useful to see deeper into the painting and see the state of conservation, when they looked at their X-rays, what they would see is especially the cradle. And I've already mentioned that we're very bad at thinking things away. And so the subtle differences to which they're trained as art conservators, art curators, to pay attention in these X-rays were virtually impossible to study in these cradled X-ray paintings. So when I saw them on the one at the Gissy, I said, but don't you find this a nuisance? Oh yes, she says it's an incredible nuisance. And hopefully she says, it would be great if you could do image processing and remove that. And I said, well, yeah, I don't know whether that's something that's worth it. I mean, it's a whole project. And so a month or so after, I was visiting Spain and the Prado. I had the privilege of going behind the scenes and seeing their image processing lab. And I said, do you have this problem too? And the conservator, very, very Mediterranean, says, do I have this problem too? And she starts pulling open drawers. She says, look, X-rays full of cradles. So I said, well, maybe then it's useful to do something about it. And we did. So to remove the cradles, you have, first of all, to locate them on the X-rays. You have to then do intensity adjust. And then, of course, once you start working, they become greedy. They said, could you remove the wood grain from the cradle, but not from the original panel? I said, come on. But we could. In many cases, we can. So this is what a cradled painting looks like, an X-ray of a cradle painting. Also, in none of these cases, we always have to work with the images that are available. I mean, you can't say, can you take a few X-rays from different angles and so on? I mean, you just work with what there is, because scheduling for new X-rays takes a long time, it's impossible. I mean, there are always many, many reasons why the digital things that they give you is what you have, and that's it. And so the first thing is that you have to find the cradle members. So you use an edge detector to locate those edges, and then we used just a kind of an equivalent of a Radon transform, well, really a Radon transform in 2D, not 3D, in order to find where things peaked most sharply, and that gave you the direction. Because, of course, even though these things had been done by master cabinet makers, they were not 100% vertical and horizontal. They were almost there, but we needed them exact. So you look at angle and you find the exact place where you line up best. And that gives you a location of the members. And you have some consistency between all of it that helps you correct if you make a mistake here and there. And then, of course, these round, I don't know whether you remember from the picture, but these hardwood members, they were nicely rounded, which of course makes the intensity change as you go through. So you have to make a nice model of that change. And we used models for the attenuation and inferred, again, because we have many places, what the likely curve was, and we used that to attenuate. And indeed, we can then remove from here on the left, which is actually from the hand altarpiece to on the right. But you see, you still have wood grain remaining from the members. And here again, wood grain remains. This is for the Gissy in the members. And they wanted to remove that. And we thought about it, and then my student Rachel Yin came up with a model that actually turned out to work in many cases. So what you can do, your image is really a painting and cradle. And for painting and cradle, you can split it in two pieces. You could have the limiters of the cradle, so the intensity, profile, and then texture in the cradle. In the painting, you could make a cartoon image and texture in the painting, but also in the wood panel. And so you have two texture components. So if you try to take the whole thing and change it into something that is intensity, patterns, and edges, and then textures, the texture pattern will have both panel and cradle. But you know that you have places where you have only one of them, because there is no cradle. And so you have places where you have cradle in one direction, cradle in the other direction, or two versions of cradles proposed on each other. So what you can do, and what we did, is we made a Bayesian modeling of all this, and then used that in order to separate. And that then led to distinguish panel wood grain and cradle wood grain. And so we can go from what we have on the left here to the right. And we were very fortunate in the Prado. So before we had the thing here on the left, and we went to the right after removing that wood grain. We were very fortunate in the Prado. They actually had a painting that had suffered so much from the cradling that they were removing the cradle and putting a very different construction on the back that had much more flexibilities, that allowed the wood to work. There it had suffered, it had made major cracks, because it was originally a sketch, an oil sketch. It was not meant to survive the ages, but it was by Rubens, so they valued it. And so since it was inferior wood, it suffered more. And so they were removing, so we had pictures before and after. We would have ground truth. This is always so hard to get in art conservation. So we looked at this piece, and this is the ground truth. This is what we got with our software, which we called Platypus, for no good reason except that everybody remembers the name. We tried with acronyms and nothing worked. And so somebody said, well, maybe something people remember, like platypus, and platypus it was. And this is what earlier Photoshop protocols, which were very painstaking and manual, led to, and so Platypus did much better. So Platypus became a software that we handed out freely and that you could download. And Noel Ocon, who was using it very regularly, unfortunately, suddenly and tragically and way too young, died in 21. And we didn't realize then that we had no person monitoring the software. And a few months ago, I got contacted by somebody from NYU Conservation and said, Platypus is not working. I said, it's not working? He said, no. And while platforms have changed, you have to keep monitoring these things. And it had changed enough that we couldn't just put our finger on and so on. So fortunately, I was spending time at the Flatiron Institute, where they have some fantastic programmers. And one of them got interested and spent half a day with it and diagnosed what the problem was, and is now working again. So, and that's it for Platypus. So, well, this is the logo, I mean, the cradle and Platypus has come out of his cradle. I am really out of time here. I'm going to flash you through projects that are more recent. One, X-ray image separation, just telling you the problem and how this is another thing. You have very different problems that come, very different questions and challenges that come out of these different application domains than things you could dream up yourself. That's another reason to do interdisciplinary interfacing with people. So back to to Ghent. This is, if you look at the X-rays of this, well, you see some of them are cradled. Some of them are cradled because they took those doors apart. They took them apart into the front and the back. And that made them thinner, and so they could display both sides at the same time. They didn't do that with the Adam and Eve panels, because this was done in the 19th century when they also thought Adam and Eve were a bit too uncovered to display, and so they had copies made that were a little bit more discreet. And so it was okay if the original naked Adam and Eve were against the wall. They didn't need those. But the result is that those panels have not been split. And so when you take their X-rays, you see both sides. So here you have Adam and the Eve panel with the back. And in order to, on the X-ray, of course, you see both of them, so you will see one in mirror. So let's mirror these. And then you see both of those superposed. Again, we are very bad at thinking things away. Art conservators find it very hard to take an X-ray that shows both and read it the way they would. So they'd like us to make two non-existent virtual X-rays that would be the X-ray if you only had one of them. Can you do that? And again, that's harder than you might think. But so here, to show you, we have the X-ray of a detail and the visuals of, and you see how you can see the eyes of Adam shining through, and the hand of the person at top shining through the X-ray there. So we have used various approaches. The best results at present are very good, but I think there might still be room for more, but it's a very hard problem. And one of the problems is that we don't have ground truth again, except if we make some. We can synthetically make some by mixing things and taking them apart, but I feel there's still a distance between synthetically mixing, and because you never know whether the taking apart comes from things that you learned through your deep neural net, because here we use the deep neural nets, and that are not immediately apparent, and it wouldn't be the first time. So here, for instance, is a detail of Eve. You see her eyes kind of shining through there, and this is what, with our best present methods, we can do. So we can do very well, but I still feel there's a little bit of drapery coming through, and maybe we can do better. So it's not a finished challenge. But of course, a bigger challenge is when you have something underneath that you don't see the visual of. So this is a painting by Goya of Doña Isabel. And again, we can do very well, but I think we might be able to do better still. So you see the painting underneath. We can separate out reasonably well, but better would be better. And then finally, hyperspectral images. So this is another joint project with a group with Pierluigi Dragotti and people at the National Gallery. This is a painting by Lippi and Botticelli. Botticelli was a very gifted student of Lippi, and so he let him already do things on very famous big paintings. And so art historians and art curators are very interested in finding details to see whether they can trace the evolution of that apprenticeship. And so they like to find the underdrawings. So you see here in the underdrawing, you see that there is the figure with the red hood. On the visual, you don't see his hand, but you see a whisper of his hand, and his face showing differently in the underdrawing. And so it turns out that underdrawing, so if you put different filters, so to be restricted to very narrow wavelengths or frequency margins, then you can actually get a lot of impression from different. So here's an example of a test panel where you can see that in some areas with some pigments you see in one wavelength you see better underdrawings, and in another wavelength you see them better under the different pigments. So it tells you that in the whole painting different layers of your hypercube will give you different information. So how from that hypercube do you extract automatically? That would really help the art conservators. One best view, one thing that synthesizes that underdrawing. And that is the topic of a paper that is forthcoming, where this is one of the results. So you can look at all these different and find the best justified. Again, not extracting a chromo, not inferring, not dreaming up, but just from the data, giving the best synthesis that is justified for art conservators. I'm going to stop here because I'm way over time. I hope I've convinced you that there are many interesting, really interesting problems where what we know and can do and helps us set up the right framework to analyze it and then to give results back to these art curators and conservators that are really useful to them. Thank you.
Thank you for showing this amazing work and sharing it with us. I have a question about ground truth. In the days before computed tomography, before CAT scan, radiologists were able to make a sort of analogous tomography by moving the detector and the X-ray source in different paths. Why is that not used by those curators to, for instance, see the difference between two layers of the panel?
So the answer is yes, it could be used, and it's not, because those are very different parts of the museum, and the people who want to try seeing things like that often, I mean, it's not, they do not govern that X-ray machine. The painting goes to the X-ray department, and X-rays come back, and that's it. You can, in advance, say, I want views with for instance, raking light, but you give all these parameters, and setting up, getting X-rays now to work with people in the National Gallery, they have to say, oh, I don't know when there's a window in their schedule, and so on. I don't know, asking for 2 exposures of the same one, plus they always, I mean, are worried about how that might ultimately damage the artwork. So taking 10 pictures of one painting with X-ray rather than 1 is not something that will be easily approved. So there are many, many reasons why we asked those questions and we were told, forget it. And we forgot it, because we won't get those.
So thank you for your interesting talk and the interesting topics that you've introduced. I have a question, or I'm just curious. So in the case of reconstructing or rediscovering the missing panel in that example, because most image processing algorithms process the images as a 2D image, but actually in a painting there are maybe textures and strokes that might be less essential in these medieval paintings, but can be very important in paintings later on, like for example in Impressionism paintings. And is there any efforts that have been made to maybe analyze these kind of strokes, and maybe to...
Absolutely, and there is, and there are, and I have not worked on this, but I know that there is literature, that there are people who are starting to do very detailed analysis in depth to get a 3D. There's also not only of the surface, but if you use much weaker lasers and you tune them carefully, you can go to different depths and you can get, again, a hypercube in depth of your painting. So yes, and people are looking at those, and I know that people, John Delaney at National Gallery in Washington is looking, for instance, at information of this type.
That's great, thank you.
Thank you for the beautiful talk. I was wondering, you were showing examples where you had to be really careful in not inventing things that were not there, right? And you showed this iterative algorithm and even experts giving you like a time
Yeah.
to stop. I was wondering, because it would also be relevant for other applications maybe, can you quantify mathematically, like give guarantees in these challenging cases where you don't have a clear ground truth that you're not inventing things?
Well, maybe one can. I don't know without having a very careful model of what ground truth would be. We haven't done that. We relied on experts there because ultimately they were going to be our guides of doing this. We actually are working on, and I'm also, a model that, like the one you're describing, I think would be very dependent from artwork to artwork, because these artists, they were so creative. With every painting they made, they learned new things. And then they applied those to the next painting. I mean, you can see how they evolved through their career. So you can't even make a model for one artist. I mean, well, for some of them, yes. Some of them learned their skill and then just cranked out the paintings. And but the ones that are most famous are often not the ones that were most successful and just cranking them out as they were working ahead. And for those of you, it's harder to make a model that will last for several paintings, and so you would have to adapt that. We are hoping to develop we have now this workflow to make a tool that would be available to volunteers worldwide to rejuvenate paintings in collaboration with art conservators. But we still foresee that they would have a channel through which they converse with the conservators to make decisions about this far, not further, that shift in RGB for this segment, and so on, because we will rely on their domain knowledge, which they can, in most cases, not accurately describe parameter-wise. So.
Thank you very much.
There's coffee too.
Thank you. Thank you for the nice talk. This question is probably not exactly in your area, but I thought I'd put this question out there. When do you think it would be possible for artificial intelligence to generate beautiful art?
Well, I think it will always lie in the eye of the beholder. I mean, in a certain sense, I feel this is not the right question, because what you mean by beautiful art, well, there's pleasing to the eye, and I think we're there already. But art at its most valuable is just like beautiful mathematics is an intellectual shortcut, and we experience that as beautiful. I think art that's really meaningful is like an emotional shortcut. It's a way of communicating between the artist and the viewer that touches you, that touches me emotionally, and I value that. And I'm not sure. I'm not that interested in that communication with an algorithm. So I don't really, it's not necessary for me. I'm not looking for it. I mean, so in that sense, for me, it's not the right question.